Hey guys, my name's Josh and I'm with the Washington State University Department of Chemistry, and I'm here to help you guys out with your lab for 102. Today we're going to be quantifying the amount of riboflavin, or vitamin B2, using UV visible spectroscopy. So, there's a few things we need to talk about before really getting into it. This molecule right here I've drawn is riboflavin. The first thing I really want to talk about is just the scale of this chemistry. These things are very small. This molecule is just a couple angstroms across, which is 10 to the negative 10th meters. So in 1 tablespoon of water, there are more molecules of water than there are tablespoons of water on the entire Earth. Let me put it this way for you. If all 7.5 billion people on Earth had 10 trillion children, there would still be more molecules of water in a tablespoon, which is crazy. So these things are really small, but we know they're there. And since we know they're there, we can kind of extrapolate their characteristics based on how it interacts with different things. In this case, we're going to talk about how it interacts with visible light. But first, I want to talk about how other electromagnetic waves can interact with the molecules. So depending on the amount of energy in light, it will interact with matter in different ways. But let's talk about the nature of light to begin with. Light is an electromagnetic wave. There's an electric wave that travels up and down, and perpendicular to that, a magnetic wave that travels with it. When chemists think about light waves, we imagine them as both particles and waves. We imagine them as particles because we like to think of little packets of energy traveling through the air in order to transfer energy. And this is what we see, is that these little packets of energy can pass that energy onto molecules. And molecules, depending on their different structures, will absorb different amounts of light. So this is the wavelength of your light. As you decrease in wavelength, you're increasing in the energy. You're also increasing in the frequency. So we're going to start out way over here with something that is very low energy. This is radio waves. This is how our phones work, how our Wi-Fi works, and everything. And then we get into the microwaves. There's a little bit of overlap. But in the microwave section, it's causing molecules to start to rotate its bonds. So the little tiny bonds will rotate and your molecules will start doing a little dance. This movement, this rotating and movement, is actually heat. In our microwaves at home, we take microwaves and shine it at water, and it causes water to shake and do all these things. See, now the reason that food kind of tastes weird when you put it in the microwave is the water can't get above 100 degrees Celsius before it goes into the vapor phase, and then we lose it. So in this case, if we heat using microwaves, the maximum heating temperature is about 100 degrees Celsius, which is hot enough to cook things, but not really do the amount of chemistry that we like to do. At high temperatures, a lot of chemistry happens, and that is where we get a lot of the flavors from our foods. So on our cooking surfaces, like your pans, or on the grill, or in an open fire, or even in your pizza oven, you can get temperatures that are local temperatures as high as around 1500 Celsius. And this is where you get some really cool chemistry happening that actually, gives to the flavor a little bit. So that's why we don't really like to use microwaves to heat up all of our food. When we start getting higher energy than microwaves, we get to the infrared region. In the infrared, which is beyond red, it's the longer wavelengths than red, it will start to cause different transitions with your molecule, depending on the functional groups that are in it. So in the case of a carbonyl group, we can have a carbonyl that has an asymmetric stretch that will go in opposite directions, and then we also have a symmetric stretch in which they'll crunch together. Well, or they'll crunch in the same direction. So using IR, chemists can get really accurate with what kind of carbonyl compounds they have. And that's really, really helpful. But today we're going to be focusing on this little tiny sliver, the visible light, and we'll get back to that in a sec. Just wanted to mention ultraviolet radiation is really handy for performing ionizations. So you shine this light on it and electrons just spew away from the molecule because the electron can't even take it when it absorbs that photon. Then once you start getting higher than that, you start really ripping apart all of your molecules. And that's why X-rays and gamma rays are very dangerous. If you go out in space, you can be ripped apart by the gamma rays from the sun very quickly. Those are the smallest wavelengths. And it's normally only given off by nuclear radiation, which is really cool. So now that we kind of know what's happening with these molecules, we're going to be focusing more in on the visible spectrum today. So in the visible spectrum, these photons between 400 and 800 nanometers can cause an electronic transition in our molecule. So these electrons that are in these bonds in here can only be in certain mathematical places at certain times, depending how much energy they have. So since these are aromatic here, the electrons are spinning around, and then they can exist in some other configuration that's mathematically allowed, depending on quantum mechanics. Spooky. Cool. So in this lab, we're going to be finding how this thing absorbs light. Now, in the best case scenario, we would have incredible instruments that could alter the wavelength of light from a very small, narrow wavelength to a larger wavelength, and then we could plot the absorbance over time in that aspect. But we're not so lucky. Our instruments can only do 4 different wavelengths, and the wavelength that we chose for this is 430 nanometers. This is a pretty good area. It's not the best, but it will still help us to quantify it. Alright, so the goal for this lab is to quantify the amount of vitamin B2, or riboflavin, in a supplement pill. So what we're first going to do is we're going to make standard solutions, and we'll talk about how to do that in just a little bit. But then we're going to make a solution from the pill itself. So we'll crack a pill in half, we'll grind it up with a mortar and pestle, and then we'll put it into a volumetric flask. The volumetric flask has a line on it that will get us to exactly 200 or 250 milliliters. So then we should know, based on, once we find the concentration, we can backtrack how many moles of riboflavin are in here, and how many grams, how many milligrams, and then trace it back to the entire pill. So for the goal of this, we're trying to make standard solutions. So we're going to start with a stock solution that's going to be provided by the stockroom. They mixed a known amount of salt with the water and will give us a concentration for our vitamin B2 solution. We'll use varying amounts of that vitamin B2 pill solution, the vitamin B2 solution, and varying amounts of water, so we have all about the same volume, but increasing in concentration. Then we'll be able to find the absorbance of each of these samples, and we'll be able to plot each of these absorbances versus the concentration. So we know this concentration here, we're finding this absorbance, and it's going to go up in a linear fashion. We have an equation to describe how it goes up, and it's called the Beer-Lambert Law, or Beer's Law. And it goes A equals epsilon times B times C. The absorbance is equal to the molar absorptivity times the path length, which is typically 1 centimeter, times the concentration. So this value right here will be equal to the slope of this line. So if we find the slope of this line, we can use the absorbance to then find the concentration of an unknown. So that's what we'll do. We'll take our pill solution, we'll try to plot it on this graph somewhere, and wherever we plot the absorbance, we will say this is the concentration. So by quantifying the absorbance of our different standard solutions, which have different concentrations, we can find the slope of this line, which is our epsilon times b. And then the Excel program will spit out a best fit line based on the slope of this line. This 4600 here is the slope, and then we have a y-intercept that's just due to some weird stuff. It's kind of unavoidable to have some kind of y-intercept. So at zero concentration, we should have zero absorption, but that's not really how it always happens, and that's okay. So now let's assume that we try to take our pill solution and quantify the absorbance, and we find that it takes 0.9 absorbance units of light in. We can plug that in for our Y value here because it connects to our Beer's Law plot, our Beer's Law equation. So we plug in 0.9 for Y, and we find our X value here, and our X should be our concentration. And we find that 1.74 times 10 to the negative fourth moles per liter of riboflavin are in our pill solution. So now if we're actually trying to figure out the number of grams of riboflavin that are in our whole volumetric flask, we need to take the volume of the volumetric flask, multiply it by the concentration of the solution inside that flask, and then we can multiply it by the molecular weight. This will give us the number of milligrams of vitamin B2 in our entire bottle of pill solution. But if you remember, that doesn't include the other half of the pill that we didn't add in. So we'll go over that next. So as I showed you, we could find the number of milligrams of riboflavin in our pill solution. We did that by multiplying the volume by the concentration and then by the molecular mass to get our number of milligrams. So we know that there are 13.10 milligrams of vitamin B2 in our pill solution. But our pill solution didn't use the whole pill. It only used about half the pill. So in this case, this is the amount of vitamin B2 in this much of the pill. So we're going to divide it by this mass to see how much would be in this pill. Then we multiply by this 0.250, which is the entire mass of the pill, to get the mass of the riboflavin in one pill. So we should see that this gram cancels with that gram, and we have milligrams of vitamin B2 per pill, and this happens to be 25.00 milligrams per pill, which is exactly what the manufacturer's label claims. So the goal of this lab was ultimately to find the amount of riboflavin in our pill, and we found that there are exactly 25 milligrams in that pill. And that's all for this lab. Thank you so much for joining us, and I hope this helped out a lot.